Okay, problem 918 says an aluminum soda can of 150 millimeters in length and 60 millimeters in diameter is placed horizontally inside a refrigerator compartment that maintains a temperature of 4 degrees. If the surface temperature of the can is 36 degrees, estimate the heat transfer rate from the can. Neglect the heat transfer rate from the ends of the can. Okay. So we have this soda can and it's lying horizontally inside a refrigerator, and the refrigerator is kept at 4 degrees C, so that's going to be our T infinity, and we're told that the surface of the can is Ts is equal to 36 degrees C, and what's going to happen is because the refrigerator is at this cold temperature of 4 degrees C, it's going to cool the can down, so what we're going to have is some heat transfer leaving that can in the form of Q dot convection, or natural convection to be more specific. Okay, so inside the refrigerated space there's no fans pushing the air around, there's no pumps, so all of the convection is just going to be based on the changes of the buoyancy forces around the can. All right, aside from the temperatures, we're also told the length of the can, and it happens to be 0.150 meters, and we're told the diameter 0.06 meters. Okay. All right. So we're going to be looking at the amount of natural convection. So in addition, there could be radiation going on in a natural convection problem, but we're going to be disregarding it, and we're just going to look at what the natural convection is. So when we do a natural convection problem, we need to have the properties of the fluid. In this case, it's air around the soda can, right? So the air properties, we need to evaluate at the film temperature, which is Ts plus T infinity over 2. So that's 36 plus 4 over 2, or 20 degrees C. Okay? So we go to the back of the book, and we find that the thermal conductivity is 0.02514 watts per meter Kelvin. We know the Prandtl number is equal to 0.7309. The kinematic viscosity, 1.516 times 10 to the minus 5 meters squared per second. And the the coefficient of thermal expansion beta is just 1 over the film temperature, where that film temperature must be in Kelvin. So this is just going to be equal to 1 over 20 plus 273, or 1 over 293. All right, so natural convection. Anytime we're doing a convection problem, well, in forced convection, we had to look at a parameter that was known as the Reynolds number. That was the ratio of the inertial to viscous forces. And natural convection is governed by the Grashof number, which is the ratio of the buoyancy forces to the viscous forces. Okay. So we have to look at this Grashof number, or the Rayleigh number, which is really just the Grashof number times the Prandtl number. Okay. Well, what is the Rayleigh number? Well, we can go to table 9-1 in our book. Okay, and table 9-1, look here. It says, well, there's a horizontal cylinder. Well, if you have a horizontal cylinder, that's what we have. We have a horizontal can of soda. The characteristic length scale is the diameter. Okay, that's the second column. And then it tells us, well, as long as the Rayleigh number is below 10 to the 12, then you can use this experimental correlation for the Nusselt number. The Nusselt number is 0.6 plus 0.387 Rayleigh to the 1/6 divided by 1 plus 0.559 Prandtl to the 9/16, all raised to 8/27, and then everything squared. Okay, so as long as those things hold true, we can use the that empirical formula from somebody's experimental work, right? So that said, I need my Rayleigh number based on the diameter as my characteristic length scale. So that means my Rayleigh number is just G times beta times Ts minus T infinity times the diameter cubed divided by the kinematic viscosity squared multiplied by the Prandtl number. So that's 9.81, beta 1 over 293, times Ts 36 minus T infinity 4 times the diameter 0.06 cubed divided by kinematic viscosity squared, that's 1.516 times 10 to the minus 5 squared, all multiplied by the Prandtl number, 0.7309. Punch that through my calculator, and I get a Rayleigh number of 7.36 times 10 to the 5. All right? So that is less than or equal to 10 to the 12. So now we can use that experimental correlation given in table 9.1. Well, that correlation was the Nusselt number for a horizontal cylinder, 0.6 plus 0.387 times the Rayleigh number to the 1/6 divided by 1 plus 0.559 divided by the Prandtl number, all raised to the 9/16, and then the denominator raised to the 8/27, and then the entire thing is going to be squared. So that is 0.6 plus 0.387 times the Rayleigh number, 7.36 times 10 to the 5 raised to the 1/6 divided by 1 plus 0.559 divided by 0.7309 raised to the 9/16 raised to the 8/27, and then everything squared. And that gives me a value of 13.39 for my Nusselt number. So now I'm still trying to find my heat transfer rate, Q dot. That is just going to be governed by Newton's law of cooling because this is convection. So that's H times the surface area times the temperature difference. I can rewrite H as the Nusselt number times K divided by D. Okay. I can rewrite the surface area. Well, this is just the surface area of a tube because I'm told to neglect the ends of the can, so it's just the tube portion. And the surface area of that tube is just pi times D times L. Okay. Then multiply by the temperature difference, Ts minus T infinity. So I see these D's cancel, and I'm just left with the Nusselt number times K times pi times L times the temperature difference. And that's equal to 13.39 times K 0.02514 times pi times L 0.150 times the temperature difference, 36 minus 4. And that's going to give me a heat transfer rate of 5.08